question. The graph shows the result of applying 500 Newton seconds of impulse to an object as it moved across the floor for 10 seconds. Determine the maximum force that was exerted. Describe the change in velocity of the object over the time interval. Okay, so same kind of thing here. Impulse, of course, is going to be the area under the curve, right? That's a triangle. So that means base times height divided by 2. Okay? So that means that the net force times the change in time divided by 2, that's the impulse. Let's see, I'll multiply both sides by 2. I'll divide both sides by time. So this F net, in other words, this maximum force that they're talking about, is going to be 2 times the impulse that they gave me, 500 Newton seconds, divided by the change in time, 10 seconds. So what would that be? Alright, so what is this? 100 newtons. Very good. Okay, 100 newtons. Then they said, describe, please, the change in velocity over this time interval, right? So let's see. From 0 to halfway, okay? From 0 to halfway along, what could you say about the velocity? What's it doing? It's speeding up, right? Okay? And from the halfway point to the end here, what is it doing? It's still speeding up, right? Okay? Because there's still a force being applied to it. Force is proportional to acceleration. If the object is accelerating, it must be getting faster. It's just getting faster at a slower rate than it was before the halfway point, right? Cool.
So if it's above the x-axis, it's speeding up.
Yes.
Alright.
Alright, so the next question is a ballistic pendulum question. So a bullet with a mass of 30 grams, not kilograms, but grams, hits a ballistic pendulum with a mass of 870 grams and lodges in it. When the bullet hits the pendulum, it swings up from the equilibrium position and reaches a vertical height of 0.74 meters at its maximum. Determine the bullet's velocity, and of course that means initial velocity. Alright, so we said that in a ballistic pendulum problem you have 2 different parts to it, okay? You cannot solve the whole thing with all conservation of momentum or all conservation of energy, right? That doesn't hold true for the whole thing. You have to break into pieces. So, the first part, where the bullet hits the block, okay, and then starts to become embedded in the block, what would you apply to that situation? Would you do conservation of momentum there, or would you do conservation of energy there?
Momentum.
Yes, we would do conservation of momentum there. Why wouldn't we do the conservation of energy?
Because it's one of those thingies you gotta do quadratic formula.
No.
No? Oh, because it has, like, no energy yet.
No, it hit the block, so it's got energy, right?
Just
Why is energy not conserved when the bullet hits the block and starts to embed inside the block?
Because the torque net is not.
Yeah, because we've got energy from the bullet being taken away, right? The friction that's created when that bullet's squeezing through the wood is going to heat everything up, right? That's stealing energy from the system, so energy's not conserved there. But momentum is, because it's a collision, right? Okay, then on the second part, okay, when the bullet is already in the wood and now it has come to a stop inside the wood, okay, this came from adding the 0.03, which just has 1 sig fig, right? Bless you. To the 0.87 kilogram block of wood, right? So, bless you. Technically, we should use like addition subtraction sig fig rules on that, but because we're then further going on and it's multiplying right here, and we're dividing by 1 sig fig here, it's 1 sig fig for our answer.
So the first velocity was solved for, what velocity was that?
This velocity is the velocity of the block of wood when the bullet is inside of the block of wood. okay, and it has come to rest inside. And this system now is going to start to swing up, okay? So what's the velocity of the bullet?
So that's just the bullet.
Just the bullet right here.
100, wait, just 160, 100 meters per second.
Very good, 100 meters per second. Does that sound like a reasonable velocity for a bullet?
Yeah.
Yeah. Okay, so an object of mass m moving in the x direction with a velocity of 5 meters per second collides with an object of mass 2m. Before the collision, the second object has a velocity of 3 meters per second to the left and 4 meters per second upward, while after the collision, its velocity is 3 meters per second in the y direction. What is the velocity of the first object after the collision? Okay, so obviously this is a two-dimensional problem, right? Because we have x and y motion. I'm going to redraw this over here for the people at home because they can't see the screen. Okay, so they didn't ask me what the x-axis velocity of this is, or what the y-axis velocity of this is. They asked me what is the velocity, right? So what does that mean I'm going to have to do?
Both axes.
I'm going to have to do x and y, and then what?
Recompose.
Recompose them, right? Okay, so we need to do conservation of momentum in the x-axis, and then we need to do conservation of momentum in the y-axis.
So whenever it's a two-dimensional, is it you just do conservation of momentum?
Yeah, because it's a collision, right?
Yeah.
Okay.
Hey, shut up, man.
630.
I'm leaving after this round.
Alright, so let's take a look at both of these in the x-axis before the collision, right? Okay, so x-axis. What would we say here for this object?
5 meters per
times
second.
5.
Right, so we would have m times 5 meters per second. Now the second object, what would we say for its initial x-axis momentum?
-3 times 2m.
Okay, good. We would say plus 2m times -3 meters per second equals, now after the collision, okay, what would we say for this object?
M times final velocity.
Okay, m times final velocity in the x-axis plus, what would we say for this one? 0, right? So I'll just leave that off. Okay? Now let's see if we can't simplify this left-hand side a little bit, right? So let's see, that's going to give me 5m plus, let's see, 2 times -3, that's the -6, right? So really 5m minus 6m, right? What's that?
-1m.
So -m equals m times v final x. So that's the thing I want right here. What am I going to do?
Isolate.
Divide by m on both sides. So what is v final x then?
-1 meters per second.
Very good. Sweet. Now we can move on to the y-axis stuff, okay? So let's see here. For this first object, y-axis initial momentum, what would you say?
0.
Nothing, okay? So the second object, what would you say?
2m times 4.
2m times 4. Let's go ahead and simplify right off the bat. What's that going to be?
8.
8m. Okay. Equals. Now let's look at after the collision. What would you say for the first object?
0. It's not moving.
No, m times final velocity in the y.
Right. M
Oh,
times
yeah.
final velocity y. We don't know what that is. We can't count that out. M times final velocity y plus, what would we say for the second object?
2n times 3.
6m, right? Okay, now let's see. This term contains the thing I want to know, right? So what should I do? Subtract the 6 from the 8. What's that going to give me?
2m.
2m divided by m? 2. Right? So that means the final velocity and the y-axis must be 2 meters per second. Am I done? Is that my answer? No? So what I have to do now? Recompose it, right? Okay, so let's see here. Y-axis is 2, x-axis is -1, so I've got -1 right here. I've got 2 right here. So that means that my resultant final velocity vector is that one. And since velocity is a vector, I need magnitude and direction. That means I've also got to get theta, right? So take a second and see if you can do that. Alright, so what did you come up with for your velocity, your final velocity?
2 meters per second at 63.4 degrees north of west.
Psych.
2.2.
I got
meters per
negative.
Oh, it's
It's
2.2.
negative
Yeah.
2.2.
At
So remember, do your Pythagorean theorem, so that means overall final
This way.
velocity
This way.
is equal to 2.2 meters per second
so
at
big.
what?
117 degrees.
117 degrees, or
Net 63.4
Hold up.
degrees
North of west.
west.
north of west.
North of
Hold up. Wouldn't it be
Why
a
don't
negative
Wait,
2.2?
why is it not 1?
Yeah, why isn't it 1, 2, 3?
Why would it
3.0.
be negative?
What do y'all mean?
In the problem, we got 5.0 and 3.0, but I just see a 4 there. Yeah, so,
Left?
yep, one sig fig.
Left and up.
They called
What?
it.
No, but isn't 3.0?
There's a 4 in there. It's just
The
straight
degree
4.
takes care of the left.
That's so.
Moving on. So, let's see, number 15.
This one seems hard.
2 hockey pucks collide. Each puck has a mass of 0.1 kilograms. Initially, puck A moved at 5 meters per second in the x direction. Puck B was at rest. Afterwards, puck A moved at 2 meters per second at an angle of 30 degrees above the positive x-axis. What is the speed and direction of puck B after the collision? Okay, so in this problem is, of course, also a 2-dimensional collision problem, which means we're going to do what?
Both axes.
Both axes, right? Conservation momentum in the x, conservation momentum in the y. But there's a little tiny catch, okay? At the end, after the collision has happened, right? You'll notice that puck A, it said, was moving off at a final velocity of 2 meters per second, but at an angle of 30 degrees, right? That means that the final velocity of puck A is going to have an x component and it's going to have a y component. So, when you do your conservation of momentum in the x-axis, right, your final momentum, let's see here, momentum initial x equals momentum final x. The initial momentum over on that other side, okay, puck A was moving at 5 meters per second, right? So it would be the mass of puck A times the initial velocity of puck A. The other puck was at rest, so it has no x-axis momentum at all, right? Okay, but now on the opposite, or on the after side, okay, puck A's x-axis momentum is going to be its mass times its x-axis final velocity. And the x-axis final velocity is going to be the final velocity times the what? Cosine of theta, right?
Oh, man,
So
it's a pink
that's
one, bro.
going to be the 2 meters per second times the cosine of 30.
So is it
Okay.
basically that puck problem, or the ping pong paddle problem we have?
Yeah,
Kinda.
there's just a little bit more to it because I have numbers in it this time. Okay, now that is just puck A. Let's look at puck B over there, right? So puck B, I have to erase this. Puck B is doing this, right? It's moving off at some angle that they have chosen not to tell me. They just said it's called theta 2, right? And they decided not to tell me what that final velocity of puck B is. That's the thing they're asking me for, right? What's the final speed and direction of puck B? I do know, however, that whatever this final velocity is, I can decompose it so that puck B will have an x-axis component and a y-axis component, right? So that means I need to add puck B's x-axis final momentum. They're both 0.1 kilograms times, now, I'm just going to say VFX right here, okay? Because I know that the final velocity in the x-axis of puck B is equal to the final velocity of puck B times the cosine of theta 2, right? So I'm just going to condense all of this into that right there and solve for just that piece. Is that okay? All right. So now let's see here. I would probably go ahead and multiply all this together and get a number, and then subtract that number from the product of this, right? So multiply this, do some subtraction, and then finally, what would you do? Divide by 0.1, right? Okay, so go ahead and do that. Multiply here, multiply there, so you can get like actual numbers. Do your subtraction, and then divide by 0.1 so we can see what V final X is. And I'm going to go ahead and actually extend that and say B, so I know it's the final velocity of B. I know that's the only unknown x-axis velocity, but I just want to be specific here. So final velocity in the x-axis of puck B is equal to... Are you going to do sig figs on this number?
No.
No, because that's not a final answer.
Oh, and then whenever you get that, you have to multiply by the cosine of 30, right?
What?
Right, Michelle?
No.
No?
Because I don't know what that angle is, right? This is the one I multiply by the cosine of 30 because I do know that that angle's 30.
So what would this number represent?
This number is going to represent the x-axis velocity of puck B.
But to decompose it, wouldn't you have to know the angle?
It's already decomposed. We're finding the x-axis. Okay? They want to know this, right? So if I want this, that means I need the x-axis piece and I need the y-axis piece, and then I can put them back together and get the overall piece, right?
Oh yeah, that's right.
Yeah, so that's what we're doing here. All right, so what is the final velocity in the x-axis of puck B?
3.26795.
3.26794. Anything else?
9.
9.5. Cool. All right, so that is the x-axis part of this. Now let's go through and do the y-axis part. Okay? Oh, I'm gonna just come over here. I've got my initial velocity y-axis. Initial momentum y-axis is equal to the final momentum in the y-axis. So before the collision happens, is puck A doing anything in the y-axis?
No.
Is puck B doing anything in the y-axis?
No.
What's the initial momentum?
0.
Alright, so 0 equals. Now let's see, after the collision has occurred, we're talking about puck A first, alright? So that's going to be, of course, the mass of puck A times the final velocity in the y-axis of puck A, right? What's the final velocity in the y-axis of puck A going to be?
2 times sine 30.
Very good, okay? 2 times the sine of 30 degrees. Plus, now we need to do puck B, right? So the y-axis final velocity of puck B is going to be what?
VFXY.
It'll just be the final y of puck B, right? So it's going to be the mass of puck B times the final velocity in the y-axis of puck B. Okay, so now let's see here. This is the term that I want, right? Or it has the thing that I want. So what am I going to do? I'm going to subtract all of this over to the other side, and then do what? Divide by the 0.1 kilograms, right? Okay. Okay, so what did you get? Wait, it was perfectly -1?
Yeah.
Alright.
Did you make this review and not know that?
Well, I mean, I solved it, but I haven't memorized my answer. Yep, maybe. Okay, so now I have a y piece and I have an x piece. What are we going to do now? Recompose them, put them back together, right? Okay, so let's see here. I have a positive x value, I have a negative y value. I expect it to look like that. And then here's my theta 2 that they haven't told me yet. Is this triangle right here, that looks like this triangle right here, since we're talking about puck B, right?
Mhm.
So that makes sense with the figure. It looks right, okay? So go ahead and figure out then what your overall final velocity is of puck B. What'd you get?
3.4.
Okay, so 3.4 meters per second. Now I need my direction, my angle theta. How am I going to get that? Inverse tangent, right? Opposite over adjacent. So opposite is the y, although don't put that negative in there. That negative is just telling you the angle is below the positive x-axis. And then of course the adjacent is your x value. And how many sig figs do we do for degrees?
3.
3.
Feel confident.
I like it.
You said don't put it in as -1?
Yeah, don't do that. So what do we get?
17.0.
Okay, so that's 17 point, you said 0?
Mhm.
Alright, 17.0 degrees. Now this needs some cardinal directions because I don't know which 17 degrees we're talking about, what quadrant we're in. So what are we going to say here?
South of east.
South of east, right? Or we could set that in relation to 0 degrees, right? So what? 343, right? At 343 degrees. Right, so either of those angles would be fine. And that's that problem. Alright, so 16, that's an elastic collision, right? So what instantly you think of what?
Conservation of
Momentum.
Conservation momentum, that's one thing
Yeah,
you should
it is.
think about. What else?
and mechanical energy.
Kinetic energy, conservation kinetic energy,
Yeah,
right?
yeah, yeah.
But there's a special formula that we came up with.
V
for
approaching equals V escaping.
very, not escaping,
Separating.
separating,
Same
right?
thing.
Good.
No, it's not.
V
I
approaching
wrote escaping.
equals V separating, right? In other words, V
I wrote escaping.
initial 1 minus V initial 2 equals V final 2 minus V final 1. Now we've done these several times already, right? So this should be pretty easy. Let's see, so I'm going to have 2 minus a negative 4 equals V final 2 minus V final 1. So V final 2 equals 6 minus V final 1. So now I've got an equation with 2 unknowns. What I need to do.
Solve for V final 2. Or solve for one of them.
Do the change
did.
momentum.
Yeah, I need to do my conservation
Momentum.
momentum, right? Okay, I need 2 equations. So here's the second equation. Alright, so now let's see here. The mass of the first object was 10 kilograms, so 10 kilograms times its initial velocity, 2 meters per second, plus the mass of the second object times its initial velocity, negative 4 meters per second, equals the after part, okay? So that's going to be the mass of the first object times whatever its final velocity is, plus the mass of the second object times, now normally we would say whatever its final velocity is. But we have solved V final 2 to be 6 meters per second minus V final 1. So we're going to go ahead and substitute that in right here. Then we will distribute. Okay? So now let's see here. 10 times 2 is 20. And 2 times negative 4 is negative 8. What's 20 minus 8? 12. So over here I've got 12 kilogram meters per second. And let's see, over here I have 2 times 6. What's that going to give me?
12.
12. And it's on this side of the equal sign, which means I'm going to have to subtract it away from the stuff that I want, right? So that'd be 12 kilogram meters per second minus 12 kilogram meters per second. So what's this going to be?
0.
0 kilogram meters per second equals, then I'll have 10 V final 1, and that's negative there, so minus 2 V final 1, so that, what's that going to give me?
0. Wait, 8.
8 V final 1, And then I'll go ahead and divide both sides by 8 meters per second. Not meters per second, kilograms. 8 kilograms. So, V final 1 then is going to be 0 meters per second. The first object will come to a stop.
Wait. So what?
Come on, son.
1 times 2, 2 times -4. 2 times
So then,
oh,
you got it?
I think.
So now we're going to take this V final 1, which is 0, and plug it in right here. So what does V final 2 equal?
6 meters per second.
Very good.
Wouldn't it be 6 plus VF1, not 6 minus VF1?
Let's see here.
Yeah, it would be cool.
Crap, yes. Oh, it's the same thing.
No, I'm talking about right there. You solved it as.
Still, okay, so 2 VF1 and 12. I would still subtract that 12 over and get a 0. That'd be 10, 11, 12 right here. That's still 0.
How'd you get 0 on the left side?
Because I did 2 times 6 is 12 kilogram meters per second. And then over here I have, let's see, 10 times 2 is 20. And 2 times -4 is 8. And 20 minus 8 is 12. And so you have 12 minus 12. That gives me 0 here. And I'll divide by the 12 and still get 0. Number 18 is the center of mass kind of question. That's not really. Alright, so we've got the center of mass is equal to, now if I look at this problem, right, it's saying I've got some person on a seesaw on one end and the other person on the seesaw on the other end.
So in that last problem, the final velocity for the second object was 6 meters per second?
Mm-hmm.
Okay.
And let's see, the first person is a 59 kilogram woman, and this one's a, 71 kilogram guy, right?
Mm-hmm.
Okay, so remember in these problems, you get to set wherever you want to be 0. So I'll say where the woman is 0, right? So that means mass times the distance, right?
Mm-hmm.
0. She goes away. So then that means 71 kilograms times the other person's all the way on the other side, and the length of the seesaw is 3.5 meters, so times 3.5 meters divided by the sum of the masses, right? So let's see, that's, 59 plus 71?
130.
Alright, so I'm multiply on the top and divide by the sum on the bottom.
1.91 meters, or just 1.9 meters.
Yeah, for 2 sig figs. Yeah, so I'm getting 1.9 meters as well.
Mm-hmm.
Okay? Alright, then let's see the next one. A car of mass m traveling at a speed v stops in time t when maximum braking force is applied. Assuming the braking force is independent of mass, what time would be required to stop a car of mass 2m traveling at speed v? Okay, so let's see here. The change in momentum is equal to F net times the change in time. Okay? and we can go ahead and expand our change in momentum so that that's mass times change in velocity still equals F net times the change in time. It said that the force is independent of the mass, okay? So that means in this problem that the force is going to be the same or constant the whole time. And if you'll notice, it said to stop a car of mass 2m traveling at speed v. It was originally v, it's v also at the end. That means that the velocity didn't change. So that's a constant, and the force is a constant. That means that the mass is going to be proportional to the time, right? And it said that we are going to up the mass by 2, right? We're going to double the mass from m to 2m. So that means that the time would change by a factor of 2 as well. Now on this next question, right, the guy is at one end of this log, and then he starts walking along, and the log's going to shift and move, right? So let's look at the before and the after situation then, okay? So beforehand, the guy, of course, has a mass of 70 kilograms times, and if you look at that picture, the guy's 1.5 meters away from the center of mass, right? So we'll go ahead and put that in there. Now, since it says in there, ignore any forces exerting on the log by water, that means there's no outside force. If there's no outside force acting on the system, then that means that the momentum is conserved, and that means that the center of mass will not move.
Yeah.
Okay? The center of mass doesn't move. So that's why we're measuring away from the center of mass 1.5 meters for that guy. The log itself, the log did not move away from its own center of mass, right? So that would just be the 250 times 0. It hasn't moved yet, because the guy hasn't moved yet. Since the center of mass, let's look at this real quick. Since the center of mass doesn't move, then that means that the center of mass before is in the same position as it is after. That means that this stuff equals this stuff, right? Let's go ahead and not find it over there yet. So if I say all of this equals all of that, then that means that I have this on both sides of the equal sign. It's like saying everybody brought mass to the party, right? Everybody brought this sum to the party in the denominators. Does that make sense? Okay, so that means that I could cancel that out. It would be like I multiplied it on both sides and it canceled out, right? So that goes away. That means that 70 kilograms times 1.5 meters is equal to 70x then minus, what's 70 times 1.5? That's this thing, right? So,
And then it's plus 250x.
yeah, plus 250x. Okay, so now let's see, that would be 250x plus 70x is 320x minus 105, and then over here, this 70 times 1.5, that's also 105, right? I mean, it has to be. Yeah, so that's 105 on this side. So you'd have, you're going to end up adding 105 to both sides.
You get 2 times.
So you end up, yeah, with 210. Then we'll divide by 320 on both sides. So x equals, and remember we're finding an amount that has been moved, so that's meters, right, a distance. So what's that going to be?
Are you here?
0.65625.
And how many sig figs do we want?
2.
2, so what is it?
0.66 meters.
166 meters.
Wouldn't you?
Cool. Okay, good job you guys.